Hello, this is Mr. Huff, and let's talk about doing some calculations with a spreadsheet for the composites lab. So we're going to start with a table that looks kind of like this. You'll have the sample information, the material, the color, what type of fiberglass we used, the width of the base, and the height all in inches, and the length between the supports in inches. And these are not the numbers from the lab. You need to use the sample map. The next thing we probably want to do is calculate the moment of inertia. We have these two values here, so we can do that. Before we do that, let's do this. If you click on this word sample or the first row at the top, and we're going to click on view and freeze one row. What that lets us do is now we can choose a column and do data and sort and data and sort. And what that does is it will sort this table without moving the top row, and that's handy. So I'm going to put that back in the original order. This way you can sort it by the types and the thicknesses and the colors and kind of clump the information you need together. Okay, back to moment of inertia. So moment of inertia is I, and it's going to be in inches raised to the fourth power. So we'll just make a little note like that. And I want it to look exactly like this column. So I'm going to click on this column, click the little paint roller, and then hit the right arrow and it paints one column over. Okay. So if we remember you should have your notes from the previous video that I is equal to B times H cubed over 12. So we're going to do that calculation right here using cell references. So we're going to start with equal, and then we're going to put a parenthesis to force the order of operations. Our base, which is E2, times, that's an asterisk, and the height, F2, and then we're going to raise that to the third power. So I'm just clicking on going to the cells that have the information in it, divided by, and the number 12. Okay, so we hit enter there, and I love that this pops up. There's a couple of ways to do it, but after I hit enter there, it sees other stuff here, and it says, do you want to autofill? Click the little green arrow. Yes, I do. Another thing is I don't like all these decimals. That's really not very helpful. So we're going to highlight those cells and hit the little left arrow with the 0, and let's reduce that to about 3 decimal places. So we've got 4 important numbers here. Okay. So now that we have that, we have to think about the other things we want to calculate or collect. So let me pause and put in some data that I get from some of the data analysis tools. All right, be right back. All right, so here's the columns that I added. I added force in pounds, deflection in inches. We're going to calculate the modulus of elasticity using a formula. And also I collected from the data the ultimate strength. So notice I have 2 forces here from our data. One is the force and deflection, and then the ultimate strength. Let's talk about that real quick. So you're going to be looking at charts that look a little bit like this, where you have kind of a straight line here, and then it tapers off, and then we have this long zone. So let's talk about what these mean. This is from up to this point, it's in the elastic zone. And right in here, let's make a dot. Right in here, this is the yield point. Bam. So right there, something changed. Okay. And then as you go across here, we're in that plastic zone where if you deform it into this, or you put enough force to get into this zone, you are deforming the part permanently. So when you take the force off, it's not going to return to its original shape. It's going to be bent. If you do that here in the elastic zone, like if you stopped right in here, then it's going to return to its original shape, undamaged. Once you pass this point, you have damaged the part. It's not good anymore. So what we want to do is we want to get 2 data points. So I'm going to change to green, and then we'll talk about where you could get your data. So One point would be the actual force that is occurring with a certain amount of deflection. In this line here, since it is more or less a straight line, you could use any point on this line and get a reasonable modulus of elasticity. Because this is a linear function at this point, you can use any combination of force and deflection to calculate the modulus of elasticity. So if you choose this one, or if you choose this one, or if you choose even the yield point, you should get a very similar number, okay? And we can go in to do curve fitting and all that kind of thing, but that's kind of more than I want to get into right now. So I just want to talk about where to choose a force. So you can pick any force along this line. Pay attention to the deflection line. It should be kind of a uniform, slowly rising line. If it's got flat spots in it, that means somebody stopped or slowed down. If it's got a curve in it, they're speeding up. So keep that in mind. Some of the samples are not real clean, okay? The other thing you're going to do is you can highlight a zone here. Let's switch to a highlighter and go to this. So what you can do is on your analysis tools, you can pick a zone and then do statistical analysis on that zone and find the max. And let's just say that our maximum was right here. And that would be, oh wow, it's tiny now. Okay, this point right here would be your ultimate strength. So the highest single value in this area, in this zone, is going to be your ultimate. So let's go back and look at our table. So these data points here in column I, I'll highlight that. These are the ones you're going to get from that zone, that elastic zone, and make sure you choose the deflection that goes with that force. And then this ultimate is going to be the highest point in the curve during the whole thing. So you'll use your statistics tools to find that max. Okay, so now all we have left to do is calculate this modulus of elasticity. So you need to refer to your notes, but you should have written down that it's going to be equal to, we're going to throw a parenthesis in there to force the order of operations, the force times the length, that's the distance between the supports, raised to the third power, divided by, open a new parenthesis, 48 times the deflection. We're using a lowercase d because I don't want to type a delta in. And then multiply that times the moment of inertia. Okay, so there is what the formula would look like for a data table like this. But you should see that this is force, length, the deflection, and inertia, moment of inertia. Okay, when you hit enter there, you're going to get that. Also, again, it's going to say, hey, do you want to autofill? So you hit check and you're done. So now we can look at the moment of or the modulus of elasticity right here, and that should be a pretty complete data table for you to analyze. So what you want to do is find the ones, group the ones that are similar together, and then make some conclusions, maybe do some averages. Like you might go over here and say, we've got all these, let's do an average. So you could just drop somewhere and say equals average, and do the things that you normally do. What I want to do is choose all these. So here's some average of modulus of elasticity, that sort of thing. So I'll let you decide what we're going to do there. All right. So, but that's a real quick walkthrough of how to use the spreadsheet to perform your calculations for modulus, or not modulus, the modulus of elasticity here and the moment of inertia here. All right. That's enough.